So welcome all to Hope Church Adult Education. 2 weeks ago, Laura Ingraham on Fox laughingly mocked Joe Biden. There you go, thank you. I, of all people, should be sensitive to holding the mic out close. Laura Ingraham mocked Joe Biden for mentioning that there was such a thing as a Webb telescope, and she laughed as if the internet could function as a telescope. And during the commercial break, one of her producers had to take her aside and said, actually, there is something called the James Webb telescope. And in fact, Science Magazine, which is the leading science periodical in the world, at the end of last year described the Webb telescope and what it's teaching us about the deep universe as the breakthrough scientific achievement of 2022. Having read a lot about this and having had the sense of, in a sense, my own smallness, but also my sense of awe at the enormity of the universe and thinking about our place in it and what is this deep space universe that we're a part of? What is the totality of the creation? I thought this would make a great adult ed forum, and who better to do it than my esteemed and just retired colleague who I was hoping might have some time on his hands, Dr. Peter Gonthier. I've known Dr. Gonthier as the person on the Hope faculty that I look to more than anybody else for his interests among scientists in the integration and the connection of science and religious faith, and Christian faith in particular. So I've had high regard for him for many years. His many years began as an undergraduate at Texas A&M, where he majored in chemistry, and then he did a PhD in nuclear chemistry, a postdoc in Germany, came back to Texas A&M, where they must have loved him, to be a visiting associate professor for a couple years before Hope snagged him in 1983. And then he spent 40 years here with us as an astrophysicist, with nearly 100 scientific publications related to his, among other things, his interests in neutron stars and the energy that they emit. He also played a key role in getting Hope into the Michigan Space Grant Consortium as the only liberal arts college in this consortium. And he's taught astronomy and the universe, and so who better to introduce us to what we're learning about the deep universe and our place in it than my colleague, Peter Gonthier.
Thank you, David. Thank you for this honor. Clear. It is a very high honor for me to be here and to share with you what's dear to my heart. And for that introduction, wow, it's going to be hard to follow that one. Yeah, so Dave asked me to do this, and of course, Dave is the ideal person to ask me to do it, and I can't turn him down. So here we are. I hope it goes well. So many faces here. Wow. Some of you I recognize. Thank you for being here. I want to share with you what I've been thinking about for many years, and what I try to encourage my students in the night sky class that I teach, but also in a senior seminar that I get to teach once in a while, and that is to integrate science and faith in some way. And if you talk to Hope College professors, they tend to say, well, they have nothing to do with each other. And I respond in saying, God is not a schizophrenic. And the students, well, they are science majors and they study chemistry or physics, and then they go to chapel, and it's, you know, how do we bring these things together? In space, the stars are always something that seems to shout at us and encourages us to consider them and what they might be saying to us. Now, yes, I had my PhD was in nuclear chemistry, but when I went to Germany for a year in sabbatical in 1990, 91, they asked me to teach, so I taught a semester in cosmology, where I had to learn general relativity on my own, and my wife says I never studied so hard, because there was a graduate course in physics. I thought it would be a general science course, but no. Then I co-taught a course in compact objects with a dear friend, and became enamored with pulsars, which are rotating neutron stars, and said, gee, I would really love to study these, to learn about them. So we got back to Hope. NASA invited Hope to learn about their JOE program, which I applied to, and was granted a grant for 3 years, and that allowed me to begin working with my colleague Alice Harding at Goddard Space Flight Center, and spent the entire summer out there in 92, 93. And then I was going with students to spend at least a month out there, typically in June, until the pandemic hit and things were shut down. And then my colleague retired from NASA and now is at Los Alamos. And so I have no reason to go to Goddard anymore. And so I kind of feel sorry about that, because the students just cherish that so very much. So what Dave asked me to do is to tell you a little bit about the James Webb Space Telescope and what these images are telling us, and some reflection on what the story of the stars is for us today. And maybe we get to finish the sentence here, okay? So the James Webb Space Telescope was put together at Goddard, and this is one of their largest clean room in the world. And as we would go to Goddard, we would see the space telescope come together. And I would get a friend to give us a tour, and he would take us around to the clean room and to where they're testing all these different satellites. And it was just a wonderful experience for the students. It's a personal thing, but it's personal in a more interesting way, and it's because of this guy here. These are 3 of my research students back in June of 2018. And the fellow that is standing, the older gentleman here, is John Matter. And he's the Nobel Prize guy for the cosmic microwave background from COBE. He shared the prize with Schmoot, and Schmoot is in Berkeley or California somewhere, and for some reason, you know, there are all these interim students that come to Goddard in the summer, and we have to have a place to sit, an office. And for 3 summers in a row, we were allowed to sit in John Matter's office. He had another office elsewhere, because this gentleman was the senior project scientist of the James Webb Space Telescope until this summer, when he basically retired from that position and now someone else has it. But the first thing I would do is sit in his chair and rub my hands over the keyboard to see if I could pick up a few molecules. Somehow it didn't work very good. But okay, so the Webb telescope was launched in Christmas of 21 from French Guiana on a rocket that took it into space, and then from there it went about 1.5 million kilometers out to. So how do I point? Does this have a laser to it or not?
It doesn't reflect well on that screen.
Okay.
You need a pointer?
No, that's all right. I'll just come over here and
That'll work.
that'll work. And given that this is being broadcast to who knows where, I'll stand up here. But in any case, this is a place where a satellite can orbit that Lagrangian point and orbit around the sun. So it's a nice stable place. There are several satellites that are out there. Gaia is out there, and recently another interesting space telescope has joined them called Euclid, which is meant to study this business of dark energy and dark matter. So that's going to be quite interesting to follow through. So it's out here, and it's an infrared telescope which allows it to see deeply into space. And of course, a telescope is a time machine. The further out that you look, the further back in time you're looking, because light travels at a fixed speed. And so it takes some time. And the further out you look, well, the closer to the beginning of the universe. As we all know, the universe started, something happened, and then comes the Big Bang a few, less than a fraction of a second afterwards. And the Big Bang is well established, and I would not refer to it as a theory, but there are certain aspects of it that maybe still remain to be theoretical. And we're trying to understand it all. So let's begin. This is one of their first images that was released on July 12th of last year. This is a Carina Nebula. It's basically a star-forming region. The nebula is basically a gas and dust, and eventually, due to gravitational instabilities, it begins to collapse and fragment and form stars, which you see in the vicinity. Now, because it's an infrared telescope, it can see through these clouds and see the stars that are behind the clouds. And that's a nice improvement here over Hubble, say, which is a visible telescope in the visible light. This is Stephan's quintet in Pegasus. So you see 5 galaxies here and a few stars, well, lots of stars. This fellow here is closer, much closer than the other 4. This is NGC 7320, that's its telephone number. 7319, 18 A and B, and 17 down here. And I'm just gonna zoom into a little square there. These images are huge because of the camera aboard. The telescope is a very large camera, and we can zoom into these images, and I guess in some case it takes a bit of time, or maybe I just turned it off. There we go. Wrong button. So we can see what you see. These are stars here that have these 6 spikes over them. These are diffraction spikes due to things that are in front of the main mirror. But galaxies here are the fuzzy ones. And so there's quite a few galaxies there. And we're going to look at one of the galaxies because they are wanting to study a supermassive black hole that is in this particular galaxy, 7319. So 24 million solar mass black hole, so they must have measured that using Kepler's third law, believe it or not. Kepler got it right. And aboard Webb is also various types of spectrographs. So you get spectra of the outer portion of the black hole or the inner portion of the black hole, and you see these different elements that are telling scientists different things. And so this is really the first time that we're able to do this. I mean, Hubble has a capability, but we're looking way in the infrared here. And we'll see that, you know, James Webb can do so much more. This is the beautiful southern ring, planetary nebula. This is what's going to happen to our sun in a few billion years, where it ejects the outer part of the sun and you have a white dwarf forming in the center. Now the center star here that you see is not the white dwarf, but the white dwarf is there. White dwarf is about the size of the Earth. And so you need to look at it in a different wavelength here, which is done with the mirror portion of the telescope. And then there's a near infrared, this is mid-infrared, and you can see the white dwarf next to that bright star there, where you can resolve it in those wavelengths. So astronomers take advantage of gravitational lensing, and what that is doing is you take a massive cluster of galaxies and it behaves as a gravitational lens. So they take advantage of that lens to see beyond, to amplify what is much further out. So this is one of the predictions of Einstein's general relativity theory, that you would see such phenomena. And the image is distorted, so they have to study the image to try to understand what is it and what is going on there and how far away it is. So this next image is such an image of a large cluster of galaxies, SMACS 0723. And this is an image that basically is an exposure for a day. And they're looking at this large galaxy cluster about 4 billion light years away. And the image is basically the size of a grain of sand that you would hold at arm's length. So it's basically, it's a 0.5 millimeter in size, 0.5 millimeter by 0.5 millimeter. That's a chunk of sky that we're going to be seeing in this image here. And there's a bunch of stars in here, and you can tell the stars. Hubble's characteristic would be 4 spikes, but James Webb now has 6 or 8 spikes if you include those horizontal spikes. But this is the image of a massive galaxy cluster that you see here, and then you see some odd shapes of things that are sort of stretched and bent out, and this is a gravitational lensing that is actually lensing an object that is beyond that. So we're talking about 13 billion light years, which is getting us close to the Big Bang itself, which is 13.8 billion years ago. So then we're looking at objects that are within a billion years of the Big Bang. And some of these galaxies that we're going to be seeing are actually a few 100 million years after the Big Bang. And so we're beginning to see the first galaxies that are forming in our universe. So we blow this up a little bit, and here you see this nice gravitational lensing, and sometimes you see multiple images of the same object, but because light is going in different paths, you're seeing it at different times, even though you're capturing it on one image. And we'll see that in a cool image later on. So here, what they have done is they've taken that image and they have looked for distant galaxies. And they're there. They just, remember, this is just an image that took a day to produce. And so they're now looking at a galaxy here that's 11.3 billion light years away, and on down to 13.1 billion light years away. So now we're saying this is what the universe looks like 700 million years after the Big Bang. So these are what you might say infant galaxies. And they determined that by measuring the redshift. And that's kind of what they're showing, what these peaks are emission lines from elements that have been redshifted way into the infrared. And I should speed up. 1040, right? Or 1130? No, 1040? Okay. Just checking. So this is our distant galaxy, and there are some further ones out that have been recently seen. And this is comparing Hubble and Webb on the Eagle Nebula. Normally, the eagle, you can see it very well here. This is the wing of the eagle. This is the body of the eagle, the head, and the feet. And normally when we image this with telescopes at Hope, we don't see this column here. And of course, we don't have Hubble, so we don't see it like this. But you can see what an infrared image is doing for us here is this same star hatchery, you might say, is producing an enormous number of stars. And this, of course, is in the Milky Way, close to the center of our galaxy in Serpent's Cauldron. So this is another thing that Webb can do for us. The other thing that Webb can do for us is look at planets. Not only look at planets, but analyze what's in the atmosphere of those planets. And this is one of the spectacular things that Webb is able to do for us, is tells us Is there oxygen? Is there carbon dioxide? Is there signs of life in some other planet out there? And this is an infrared image of Jupiter. We recognize that one. There's Saturn with a couple of its moons, including this Enceladus. And Enceladus, it has this frozen surface sitting on an ocean of water. A lot of these moons are this way. Europa is a moon of Jupiter, and basically what NASA's going to wind up doing is going to Europa soon, going into below the ice and search for bugs. And, it could be that the whole genome can be analyzed at some point of these bugs. Suppose we share a common ancestor with the bugs. Now what do we do? Huh? Where does life begin? But in any case, sometimes because of the tidal interaction with Saturn, Enceladus has these cracks in the ocean where these plumes of water vapor come out, and we've known that, and so does Europa have that. And so there's a torus of basically water vapor as Enceladus orbits Saturn, and there's one of the plumes on that image on the left there, and Webb is able to analyze that light that is going through that plume and establishing that there is water there. So okay, we have water in Enceladus, and we know that. This is Fomalhaut. This is a bright star in our sky. It's in the southern horizon in our evening sky right now, down low in Pisces, Australia. It's 25 light years away, so it's nearby. But what Webb is doing is it's blocking the light out of the main star because it's so bright, in order to see the protoplanetary disk that is around it. And you can see already that there's coalescence of that material in the process of forming a protoplanetary protoplanet, you might say. And pretty soon it will clear all that up, and we'll have a solar system around Fomalhaut. Most stars are that way. Most stars, it's the common feature of their formation with a cloud of dust and gas that is collapsing under gravity. There's usually some motion, orbital motion to it, and the smaller it gets, the more rapid it rotates, flattens out into a pancake, forming a protoplanetary disk. And typically isolated stars are going to have planets around them. There's already, the count is over 5,000 already, the exoplanets that have been discovered. And this is one called WASP 96b in the constellation of Phoenix. The planet itself is a large planet, about 1.2 times the mass of Jupiter. It's also a hot planet, and so it's close to the star. And the planet eclipses the star, and there you see the dip in the light coming from the star. And as this planet goes in front of the star light is going through the atmosphere of the planet. And so what Webb does is it looks at the atmosphere to be able to analyze and see what's there. And this is the first time we've been able to do that. So this is a spectrum of this planet, WASP 96b, showing clear evidence that there's water. And no surprise, producing a star produces an enormous amount of water. And we have such water all over the place in our solar system. So that's not terribly exciting, but okay. This is a different WASP 39b, and this is evidence that there's carbon dioxide in this atmosphere of this planet. And so what does that tell us? Well, it could be volcanic. Doesn't necessarily mean that they're aliens there breathing oxygen and producing carbon dioxide, you know. That's not necessarily a sign of life. Now, this is an interesting planet. It's K2-18b, 8.6 Earth masses, 120 light years away in the constellation of Leo. It orbits a red dwarf, 33-day orbit. It's in a habitable zone, which means it can have liquid water on the surface. And so they take a spectrum of its atmosphere and they find dimethyl sulfide. And the only thing we know that produces dimethyl sulfide on Earth is life. Now that is not a sign necessarily. There's always something we've left out. So it's not going to convince anybody. But it's interesting. This is the Crab Nebula. Crab Nebula is a supernova remnant that exploded in the constellation of Taurus in 1054 AD. It was recorded by Chinese folks who kept catalogs of these transient events occurring in the sky, as usually seem to suggest not a very good omen. So they probably got their pots and pans out and started banging them to chase it away. And it worked. Couple of weeks, it's gone. But this is a filamentary structure, and what is new here is this kind of grayish that Webb is able to do for us in the infrared. This is coming from the synchrotron emission from the neutron star that is in the center of this, somewhere in there. Neutron star is only about 10 kilometers in radius, 16-mile diameter star, size East Lansing. I'm going to make use of this water here. Excuse me a second. So let me blow up the center of this. I'm not entirely positive, but this guy here, now normally you wouldn't see the neutron star in infrared because the neutron star's surface is about 1,000,000 Kelvin and it's emitting soft X-rays, so wrong telescope. We need Chandra. Now I'm going to spill this. Watch me. So this is an interesting image because it's showing us a star 13 billion light years away. That's 13 gigalight years. And it's a gravitational lens of a massive globular galaxy cluster. And this is the image here. And you see the star here, sort of 4 well-defined spots. It's the same star, but it's way beyond this massive galaxy cluster. And that's the name that they gave it for whatever reason. I guess it's a famous name from,
Lord of the Rings.
yeah, okay, there you go. One that I missed. Okay, this is another interesting image of a black hole. Very early in the universe. So this is 13.2 billion light years. So 600 million years, and we already have a supermassive black hole. We don't know the mass, but they know that it's a massive black hole because the only thing, it's not so much the Webb image, it's the Chandra image. These are X-rays. And so you have material that the black hole is accreting, soaking up, and in the process, that material radiates X-rays. And so that's fascinating, and one of the questions is that we really don't understand how you can form a massive black hole quickly. Because normally we think, okay, you start out with solar mass black holes and they grow. But now they think that's what's happening is you have a huge cloud of dust and gas that will collapse directly into a black hole early on in the universe when things are interacting in much differently than they are now. So that's interesting. This is a globular cluster in Hercules. Globular clusters are orbiting the disk of our galaxy. There are about 150 of them in our Milky Way. And given the distribution in the sky that told astronomers in the 1900s where we more or less were relative to the center of the galaxy. But it's interesting here because this is a Hubble image, and now we bring in a Webb image, and of course this is just a tiny part of the globular cluster. But these are old stars, and how old are they? Well, they're of the order of 13 billion years old. This is an HR diagram, so you plot the brightness of the stars versus their color. And these are what are known as main sequence stars, and the mass increases in this direction, and the heavier, the more massive the star is, the shorter its lifetime. So the massive stars have moved off the main sequence, and this particular turnoff point here, as it goes off the main sequence into the subgiant branch, this is a red giant branch where they become red giants. That particular, so this is between 16 and 12, which is 14, it's roughly. They formed at the very beginning. And they seem to be related to the structure of our Milky Way. Okay, 10 minutes away. Okay, so this is a Hubble Deep Field that came out back in 2011. And we have a nice quote here. It says, these observations provide us with the best insights yet into the early primeval objects that have yet to be found. Richard Bowens. And so who is this Richard Bowens guy? Well, he was a friend. He was a student of ours. Graduated in '94, first author of this Astrophysics Journal paper. And this is the image of a galaxy that is 13.2 light years away. That's its telephone number in case you want to learn about it. This is basically a sand grain at arm's length, that image. And this was the image, and usually I show this to my night sky class, and I asked them, when you look at this image, these are all galaxies with the exception of a couple of stars. Here's one, and here's another. The rest of them are galaxies, about 10,000 of them in this picture alone. How does that make you feel? Who are we, says the psalmist. And yet he who called out each one of these by name and placed it right where it belongs, not only these galaxies, but the stars in the galaxies, yeah, came here to shed his blood for you, for all of us. Only at Hope College can I give that message to my college class. Well, from this image we can estimate the number of galaxies visible in, well, maybe. All right, here we go. So it's a 2 by 2 arc minute image, and we can figure out, okay, suppose we look at the entire sky, we would find 370 billion galaxies in the observable universe, and that's the number there. And each one of those galaxies has, well, about 100 billion stars. And that's a little bit conservative. So you multiply those two together and you get 3.7 times 10 to the 22, or 3, 7, and 21 zeros following that. That's a big number, you know? This is a comparison of Hubble, that deep field, ultra deep field, 11.3 day exposure, and this is less than 1 day of Webb. And they're seeing the same deep field. So imagine what Webb is going to do when it starts looking for a few days. Right now is not the time. There's obviously more important things that Webb is up to. Okay. This is an interesting image because it's a gravitational lensing, again, of some galaxies. These three images are the same region in the sky, way behind it. And there's a supernova going off in one of them, but it's not there in the others. So this is supposedly 100 days, 1,000 days later than this image, and this is 320 days later than this image. And yet they're all being caught in the same image, but they're just going in different paths. It's pretty incredible what one can learn from these. And this is a recent paper that came out showing galactic evolution, the evolution of galaxies from about 10 billion years ago to 13 billion years ago. And we see a nice, fairly nice big galaxy there. And now we're looking at a kind of a red smudge, and that's about all. So we're trying to understand galactic evolution there. So how big is the universe? This is the observable universe. Oh, okay, I think we have time. I was beginning to hurry, and it's not at 10:30, it's 10:40, okay.
Questions? Save time for questions.
Yes, that's right. Okay, we'll end quickly here. The Milky Way, okay, so we figured out the number of stars. In the observable universe, and who knows how much bigger the universe is. We can only study what we can see. But somebody had way too much time on their hands, and they decided to calculate the number of sand grains on all the beaches of the earth. And so how do you do that? Well, you need GPS, and you need to make some estimates, and somebody did that. It's out on the web, and they came up with a similar number. About 10 to the 22. Now, we've all walked on the beach, right? Even with our bare feet. But how many of us picked out a sand grain and said, oh, look how beautiful this is. I'm going to take it home and put it in a special place so that I could admire it. But isn't that what we're doing? The story is not about us. The story is about Him, who made all these stars and put them in the right place. If we take the age of the universe, 13.8 billion years, and scrunch it into 1 year, so we make the scale, and we say, okay, let's do that. This is also from my night sky class. So, okay, the solar system winds up forming. It's about 5 billion years old, so it forms around August of that year. Life begins on Earth around September 15. El Día de Grito, Mexican independence. Phytoplankton begin to oxygenate the atmosphere on October 12th. So now we can end life on the land. On December 26th at 7 p.m., mammals show up, big mammals, beyond the dinosaurs, yeah. On December 31 at 11:52 p.m. and 30 seconds, modern humans show up and have been around for 7.5 minutes of that year. Who are we? How do we figure into this picture? My life has only been 0.16 seconds of that year. Sometimes these scale things help. Well, it's not about us, it's about Him. Psalm 8, when I consider your heavens, the work of your fingers, the moon, the stars, which you have set in place, what is mankind that you are mindful of them, human beings that you care for them. Imagine the psalmist now looking at some of these web images. Psalm 19, the heavens are declaring the glory of God, and the skies proclaim the work of His hands. Do we see that? Do we hear them? Day after day they pour forth speech, night after night they reveal knowledge. They have no speech, they use no words, no sound is heard of them. Yet their voice goes out into all the earth, their words to the ends of the universe, he would probably say. He determines the number of stars and calls them each by name. All 3.7 times 10 to the 22 of them. Isaiah, lift up your eyes and look to the heavens. Who created these? Who brings out the starry hosts one by one and calls forth each of them by name? Because of his great power and mighty strength, not one of them is missing. So, that's the story of the stars, at least according to this physicist, okay? Next week, what I would like to do is look at the story that a different book gives us, the book of Scripture, and how might this story of the stars, particularly the physics, the laws of nature, pertain to Scripture and what Scripture teaches us. And the word Emmanuel is going to be big on that list. God with us. So my way of integrating, and it's the personal view of this physicist, that would allow us to enlarge our understanding of the presence of God with us. And so, questions? We have 10 minutes or so.
We're being recorded, so be aware of that.
Okay. Fred over here has a question.
How does the possibility of multiple universes fit into this pattern?
Some people might say that because our universe is so special, and the specialness of a lot of things in our universe, constants of nature and so forth, seem to be accidental. And so how do you explain it? The universe has to be the way it is because we're here. It has to have the certain characteristics for life, and so maybe we're one of many, many universes. Now, in reality, there is this inflationary period to the Big Bang that is controversial. It's a theory that we had this rapid expansion that takes place before the Big Bang. And it solves a lot of problems, so it may be true. And there's beginning to be evidence that it is. The theories that people have produced, and there's many of them, happen to say that the universe replicates itself. And if it's going to do it once, it's going to do it many times. And that's where this multi-universe business comes out of. It's not necessarily because they don't want to say, gee, look, it's designed this way because we're here. There is a designer, a grand designer, which we believe to be the creator. But that would be metaphysics for a scientist. And so, now it could be that that's the way that God did it. Shouldn't necessarily surprise us. Don't know. And the issue is we can't probe those other universes, so is it really a matter of science to begin with? It's a good question, yeah, very good question.
Dawn Volkins, you have a lot of emphasis focused on the past to the beginning.
Yes.
Is anyone turning around and looking the other way to look toward the end?
Oh.
Or the
Telescopes can't do that for us. The time machine only works backwards. The future, no magic to that.
But there are things newer I don't know, I know before and behind doesn't work. You're looking back, there are things that are older than us, but we are not the newest. There are newer things behind us yet. Is anyone looking out rather than in?
No, well, there is no out. There's always in. And there's always going to be a time lag because it takes time. So you're always looking in the past. We can't look somewhere out there and see the future because the future's not there. The universe is expanding, and at some point we'll be there. Tomorrow is not yet here. So you can't look to the future anywhere. So I don't know where that comes from, but
Russell Dykstra, we've known each other from Hope College.
yes.
I'd like your idea of the potential for divine intervention if I connect that we may not be the only life in the universe,
Yes,
but we may be the first life in the
that's
universe.
true. There's Fermi's paradox that says, okay, if there's other intelligent life, where are they? And some people say, well, they've been here. There are all these interesting UFO stories. They must be true. Not sure. They're releasing a lot more and more of the UFO business that they have kept secret. So who knows? I think there's a lot of unexplained phenomena. That doesn't mean that it's alien life necessarily. We could be the first, since we haven't seen anybody else. It's taken us basically 5 billion years to come around. So, you know, why has not that happened elsewhere in our galaxy? Which it could have easily been another 5 billion years somewhere else. If life is abundant, why not? Intelligent life is self-selecting. It's obviously a good thing to have intelligence, so it will be selected out as a benefit. But I don't know. Your guess is as good as mine.
Jane Dickey, over here.
Yes,
Um,
Jane.
So we know that stars die,
Yes.
and so, of course, any planets around them also.
Yeah.
Do galaxies have a lifespan?
Well, because they're stars within the galaxy, then obviously they have a lifespan as well. Eventually, all the stars will fizzle out. And either they will remain as neutron stars, white dwarfs, or black holes, and that's the end of the story. Maybe everything coalesces. You know, we have about 3 to 5 billion years left of the sun, and then it's going to expand into a red giant, and the Earth will go around the sun inside of it, and life on Earth will be done. So it's a good motivation to go elsewhere. But around that same time, the Andromeda Galaxy is going to collide with our Milky Way, and there's going to be sparks everywhere. Could be that Earth survives that, but it won't survive the sun. So this is another story of the stars. Everything in the universe has an end in sight. It was created with a beginning, and as it is created, its end is marked for sure in it. And so this universe is not the universe that Scripture mentions as one in which we can be there forever and ever. So what's up? Well, there has to be a new heavens and a new earth.
That's a wonderful line on which to close, but I must ask one more question, and that is, based on what you've just been saying, much of what we've been seeing in these pictures no longer exists, correct?
Yes.
And so, and there's probably other things out there that we can't see because they're too far away to see them,
Yes.
that have been born since.
Yes. What we can see of the universe is what is called the Hubble Observable Universe. We can only see as far back as there have been time.
So we're looking at the history of the universe.
Yes. We can't look beyond it.
Right. Well, is this fascinating or what? Join me in thanking Dr. Gump here. We look forward to next week.